Hi, I'm Reshmi, and I'm a fourth year graduate student at the Makri lab at the University of Illinois Urbana-Champaign. Urbana-Champaign are twin cities located about 2 hours from Chicago, and it's pretty amazing to live here. So, right from my undergraduate days, I was very interested in quantum chemistry, and that is what I wanted to do in my future. So, that is how I ended up here at the Makri lab. So, before going into details about my research, we know that when we go from the macroscopic world to the microscopic world of atoms, things are not the same anymore, and we shift from classical mechanics to quantum mechanics. Now, in quantum mechanics, as the system size increases, it scales exponentially, or in other words, that the calculations become much more intractable. So, our group has been working on methods which can actually deal with larger system size and not have to have the problem of exponential scaling so that the calculations are much more feasible. So, to present an overview of the research that I have been doing in this group, I move on to the slide. So, our group deals with quantum dynamics, and more recently, we have been interested in extended systems, which are systems that contain repeating units of the same or different monomers. And we use the path integral formulation of quantum mechanics for that. So recently, the group came up with a method called the modular path integral, or the MPI. And the advantage of this method is that it gives a linear scaling with system size as opposed to exponential scaling, and that makes the calculations much more feasible. So another thing to consider here is that a system is never isolated. It always has an environment which it interacts with. So our group, this method also helps us with that. And we can add an arbitrary number of vibrational modes to the monomer at a negligible extra cost. So we can see that pictorially depicted here, where the spheres are the monomers and the cloud around them depicts the vibrations or the interactions with the environment. So I specifically have been working on the quantum Ising model. So the quantum Ising model is a theoretical model, and it can be used to describe systems such as magnetic spin chains or qubits, which we know form the basis of quantum computing. So what exactly are we trying to study here? So we just want to see how a quantum Ising chain behaves in the presence of a dissipative bath, and how does that help us. That actually helps us in understanding systems like I mentioned before, like magnetic spin chains. So if we have a chain of monomers where every monomer acts as a magnetic center, so the bath that we include with these monomers can actually mimic the monomer vibrations, and that can give us useful information about how these magnetic systems behave in time. And also, we know that computing the qubits from the basis, and due to interaction of these qubits with the environment, there is a loss of information. So our methods can actually help us understand this much better, and we expect to know more about these systems with our methods.